All right, let's work through these homework problems. So, number one, scientific method is a process that scientists use to understand the physical world. Place the four basic steps of the scientific method in the correct order from start to finish. So, you start with an observation, right? Then you formulate a hypothesis. Then you evaluate the predictions. Then you adjust. You don't adjust results to agree with popular opinion. Then you report the outcome. So we never adjust the results just to curry favor with the overlords. SI unit of each of the quantities, mass, kilogram, length, meter, times second. Identify the power of 10. That defines each of these prefixes. Input your answers as 10x, where x is the power of 10. So nano is -9, centi is -2, milli is -3, kilo is 3, micro is -6, mega is to the positive 6. Write the name of the metric symbol prefix associated with each mathematical factor. Do not use any hyphens in your answers. Do not abbreviate any prefixes. Spelling counts. This would be nano, milli, centi, and kilo. Label the zeros in this number as either significant or not significant. Okay, so the first two zeros are not significant. The last zero is significant. Okay, label the zeros in this number as either significant or not significant. Same thing. The last one is significant. The other ones are not significant. Oops. Not significant. Not significant. 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 Okay, check. Good. So, significant figure means it's part of the number, part of its precision, part of its whatever. Leading zeros don't matter. We don't care about them. But 0.0205 is very different than 2050, because that means you know the precision to 1, 2, 3, 4, 5 digits instead of 4. So it tells you about the precision, which is why we care about it. Okay, significant, not significant, same thing. The first two zeros are not significant. The other ones are the same thing. Just do that a bunch of time. Convert 8.49 kilometers to centimeters. 8.49 thousand meters into centimeters. You do 8.49 thousand centimeters. Meters times 100 would get you how many kilometers? How many centimeters in that many kilometers? Speed of light is this. What is the speed in kilometers per hour? That's just a unit conversion. We've got 2.9 times 10 to the 8 meters per second. We have to convert seconds to hours and meters to kilometers. So you're going to multiply it by 2 conversion factors. Consider a cloudless day. The sun shines down in the U.S. If 2,798 kilojoules of energy reaches a square meter of the United States in 1 hour, how much total energy reaches the entire United States per hour? So if we just do this real quick, we have 2,798 kilojoules per square meter per hour. How much energy reaches the entire United States per hour? This is going to be multiplied by 9,158,960 kilometers squared. And then you've got to convert from meters squared to kilometers squared. So you're going to do 2 conversion factors from kilometers to meters, but twice to get your answer. And once you get these units in the same dimension, they'll cancel out, and then you'll just be left with kilojoules per hour, and then you'll get your answer. Okay, next. If caffeine concentration in a particular brand of soda is 2.61 milligrams per ounce, how many sodas would be lethal? Okay, another conversion factor. 10 grams is a lethal dose, 12 ounces in a can. So you want to figure out how many cans. Well, first of all, you figure out how many ounces will kill you. So how many ounces are in 10 grams of caffeine, and then go from there. Okay. So convert 87.9 meters squared to square centimeters. Again, you'll just convert from meters to centimeters twice. The volume of a sphere is given by the equation V equals 4/3 pi r cubed, where r is the radius. Calculate the volume of a sphere with a radius of 705 picometers in cubic meters. So you'll just say V equals 4/3 pi, and then R is 705 times 10 to the minus 12 meters cubed. Okay, you do that, and that's your answer. Done. Soccer field's vary in size. The soccer field's 115 long and 89 wide. Assume that 1 meter equals 3.28 feet. What are its dimensions in feet? Okay, so 115 divided by 3.28. Times 3.281 will give you the length of feet, width in feet, and then multiply that by 12 to get your inches. Football is on a 100-yard line. What is the length of the field in meters? Okay, so you know it's 50 yards, but that's not exactly what a meter is, so you do 100 yards, convert that into feet, 3 feet in a yard, and then once you have feet, then convert it into meters. All right, round each number to 3 significant figures. So the first one is we want to stop at the 5, so it should be 0.0365. And the next one, 1,044.987, and then the last one, 4.0007. That would be 4.001. Okay. Next, in infants, I think this one, 4.00. Yep. Okay, so an infant's pulse rate is measured to be 135 plus or minus 4 beats per minute. What is the uncertainty in this measurement? The uncertainty is plus or minus 4. What is the percent uncertainty? That's going to be 4 divided by 135. That'll be your percent uncertainty. Okay, so if you have 135, 4 divided by 135 is the percent uncertainty. Okay, how many significant figures should each answer be rounded? So there's your equation, and the way this works is that if that's your unrounded answer, you keep the precision of the least precise value you have. In that case, both of these have 3 digits after the decimal, so we'll keep this to 4.113. Okay, so we'll round it to those 3 significant digits. Okay, so after rounding, the equation A should have 3 significant figures. Oops, delete that. Okay, so then delete, screenshot. Same thing here, equation B. 0.18 is the finest resolution we have there, so we're going to keep it to that second digit place. Okay, so and then is that the rest of that problem? Okay, yep. Next. Typical person has an average heart rate of 74 beats per minute. Calculate the given questions. How many beats does she have in 2 years? How many beats in 2.00 years? And finally, how many beats in 2.000 years? Play close attention to significant figures. Okay, 74 beats per minute, 525,600 minutes in a year. So multiply that by 525,600, and that'll be that number of minutes in a year, and then divide by, to get years out of it, and you'll just keep changing the significant figures from multiplying it by 2.0, multiplied by 2.00, multiplied by 2.000. So you'll just keep 1, 2, or 3 significant figures. Blood pressure is this. What's the percent uncertainty? 8 over 125. Assuming the same person, the same device, uncertainty is 91. 91 times that same percent uncertainty will be the uncertainty. So in the first case, you do 8 over 125. In the second case, you do whatever the result of that is times 91, and then that will become your uncertainty. According to the United States Department of Agriculture, Texas had this many dairy cows. If one cow produces this many grams of methane per day, how much methane was produced by dairy cows in Texas in 2013? Okay, 435,000 dairy cows times 201 grams per day per cow will give you the amount of methane produced. Stationary camera takes a long exposure picture of a ball lit by a strobe light, evenly spaced time intervals. Resulting picture is shown in the diagram. The number by each image indicates the strobe flash that illuminated that particular image starting at 1. So that's a description of the motion. So the ball started faster, and it looks like it's slowing down because it's okay. The position is the same amount of time. The position is staying the same, so the rate is not select the correct description of the ball's motion. Okay, the ball is slowing down. Next, person is initially driving a car east down the road. The magnitude of instantaneous acceleration is increasing with time. The direction of the acceleration is always to the east. Okay, so they're moving to the east. The acceleration is increasing. The direction of acceleration is to the east, so the car is speeding up. It's just increasing, constantly going up. Same thing, car is driving east down the road. The magnitude of the acceleration is increasing with time, but the direction of the acceleration is always to the west. So that means the car is going to decrease. So if we look at it like this, the car is going this way, the acceleration is that way. The car is going to, as time goes on, that velocity vector is going to shrink and decrease, but then the velocity vector is going to start getting bigger. Okay, so you're going to slow down, turn around, and start going the opposite direction. All right, and then we've got the question again, but car's driving to the east. The magnitude of acceleration is decreasing with time, but the direction of the acceleration is always to the east. So even though the car is driving to the east, the acceleration is to the east, so it's going to be speeding up because the acceleration is in that direction. Even though the acceleration is getting smaller and smaller and smaller, it's still speeding up. So in the first second, it would go from 70 to 80. And the next second, it would go from 80 to 85. And the next second, it would go from 80 to 88. The next second, it would go 88 to 90, 90 to 91, 91 to 91.5, and so on. So it's still speeding up, but even though the acceleration is decreasing, it's still positive in that direction. Okay, same thing. The direction of the acceleration is always to the west. Speed of the car, same thing as before. Since we're moving east and the acceleration is constant but to the west, we're going to slow down and turn around and go the opposite direction. Okay, baseball players warming up, toss the ball straight in the air. The ball travels up until it reaches a maximum height and then falls back down to the player's hand. If air resistance is neglected, then the magnitude of the acceleration of the ball is what? So toss it straight up in the air, goes until some height, falls back down, air resistance is neglected, the magnitude of the ball, it'll be the same throughout, constant in all forms of the flight. 5 students are asked to draw a motion for a baseball falling downward after being released from rest. Each student draws a different diagram. Which one is correct? So it's going to start, and it's going to initially be close to the initial position and then slowly increase. So from my viewing of this, N is the only one that has the correct diagram to show what's going on. Okay. Next. The figure shows a position versus time graph for a moving object. At which point is the object moving fastest? So that's going to be when the slope is steepest, and the steepest line occurs at D, because at point A, no velocity, at point C, no velocity, at point B and D, you have velocity, but D is steeper. Your rate of change is higher, so it's faster there. Figure shows a position versus time graph for a moving object here. At which point is the object moving the slowest? So if our position versus time graph here shows you where it's moving the slowest, it's going to be at point B, because that's when the person stops and turns around. So they're actually going to be stopped at that point. Okay, even though the position versus time at point D, the position is 0, the velocity is not 0 because the slope at that point is not 0. So keep that in mind. Squirrel runs along an overhead telephone wire, stretches from the top of one pole to the next. It is initially at position 2.19 meters as measured from the center of the wire segment, then undergoes a displacement of 6.919 meters. What is the squirrel's final position? Okay, so we start here at 2.19 meters, and then, so this would be 0, and then he walks negative 6.19 meters that way. So we're going to take 2.19 off that, and so from here to 0 is 2.19 meters, which means we're going to have 4 meters left to walk, so we should end up at negative 4 meters at the end of that thing. Okay, when throwing a ball straight up, what is correct about the magnitudes of its velocity and its acceleration at the highest point in its path? So you throw a ball straight up, the velocity and acceleration at the highest point. So at the highest point, the velocity is 0, and the acceleration is always negative 9.8 meters per second squared. Or in this case, we're talking about the magnitudes, so we don't care about the minus sign. Okay, so V is 0, But acceleration, even though v is 0, you're still going to fall. You're not just hanging out there when you get up there. You're still falling. Okay? So it's 9.8. Classify each quantity as a vector, scalar, or cannot be determined. So a scalar, arrow A is a vector, right? 13.8 meters per second south is a vector. The last three are scalars. Okay. The speed of propagation of the action potential in a nerve depends on the diameter of the fiber. If the nerve cell connecting the spinal cord to your feet is 1.2 meters long and the nerve impulse speed is 18 meters per second, how long does it take for the nerve signal to travel the distance? Which is just the rate times time equals distance equation. Jack and Jill are in a pool. Jack swims 9 lengths of the pool in this many seconds. Jill, first faster, covers 10 lengths in the same time interval. Find the average velocity, average speed of each swimmer. So 9 lengths, 142.7 seconds. Each length is 25 meters, 25 times 9, total distance. Rate times time is distance. That'll give you your average velocity for both of them, and you can do that. A gnat takes off from one end of a pencil, flies around erratically, like flies do, I guess, or gnats, for 38.1 seconds before landing on the other end of the same pencil. If the gnat flew a total distance of 4.65 meters and the pencil is 0.0563 meters long, find the gnat's average speed and the magnitude of the gnat's average velocity. So, what you care about here, the average speed and average velocity. So you've got a pencil here, you got a fly, and the fly is going to go and end up over here. Okay, so the time is 38.1 seconds. If the gnat flew a total distance of 4.65 meters and the pencil is 0.0563 meters long, find the gnat's average speed. That's going to be average speed, rate times time equals distance, so distance over time will be your speed. Average speed is going to be 4.65 meters divided by 38.1 seconds, but your average velocity is going to be 0.0563 meters divided by 38.1 seconds, because this distance is what you use for the velocity, but this distance is what you use for the speed. Okay, delete. Next. A cheetah can accelerate from rest to a speed of 30 meters per second in 3.5 seconds. What's acceleration? Change in v over change in t. So 30 meters per second minus 0 divided by 3.5 seconds. That's your acceleration. After an acceleration of 3.47 meters per second during this time, a car reaches a velocity of bliss. Find the car's initial velocity. So we've got an average acceleration of 3.5 during this time. So v final equals v0 plus acceleration times time. Our final velocity is 14.7. Our initial velocity is, plus 3.47 meters per second squared times 2.15 seconds. So bring the v0 over here, or bring all this stuff over there, whatever you want to do. Solve for v0. So we're going to have v0 is equal to v final minus acceleration times time. To get it back, we started with this velocity. We're going to subtract everything we just did. We're going to rewind back to our starting point, and then you get your initial velocity. Okay, halfway there. A black mamba snake has a length of 2.82 meters and a top speed of 3.72 meters per second. Suppose a mongoose and a black mamba find themselves nose to nose. In an effort to escape, the snake accelerates 3.07 meters per second from rest. How much time does it take the snake to reach its top speed? So it's got a top speed of 3.72 meters per second, and it can accelerate at a rate of 3.07 meters per second squared. Use the same equation. V final, our initial velocity is 0. Solve for t using this acceleration. How far does it travel? We're going to use another equation. You could use two equations. You could use v final squared equals v initial squared plus 2ax to solve for the distance the snake flies away. Initial velocity of 0, final velocity of 3.72 meters per second. Or you could say the distance is going to be v0, well, that's 0, 1/2 at squared. That's it. And so if you figure out what your t is, how far is it going to travel in that time, given the fact that it's accelerating at that rate from rest, you can calculate that. Okay. Next one. Dr. John Paul Stapp was a U.S. Air Force officer who studied the effects of extreme deceleration on the human body. On December 10, 1954, he rode a rocket sled and was brought jarringly back to rest in only 1.4 seconds. Calculate the acceleration. You've got a final velocity and an initial velocity and a time. So your final velocity is 0, your initial velocity is 282 meters per second, brought to a stop in 5 seconds. You can calculate what G is, or A is for that. Once you get A, you divide by 9.8 to get it in terms of G. How many times, when you're a fighter pilot, how many G's did you pull? How many G's is your roller coaster? That's the acceleration compared to what you're used to at rest. Calculate as deceleration and express it in multiples of G. Okay, so you go from 0 to 282, 282 to 0. In the first case, it's 5 seconds. In the next case, it's 1.4 seconds. So you'll have 2 accelerations. A swan on a lake becomes airborne, flapping its wings and running on top of the water. If the swan must reach a velocity of 6.5 meters per second to take off and accelerates from rest at that rate, what distance does it travel before becoming airborne? So you have your v final squared equals v0 squared plus 2ax. You've got an initial velocity of a final velocity of 6.5 meters per second, an initial velocity of 0, and an acceleration of 0.35 meters per second squared. Solve for x. Okay, and then you can solve for t from there. Blood is accelerated from rest to a speed of 30 centimeters per second, a distance of 1.77 centimeters by the left ventricle of the heart. Determine the magnitude of the acceleration A of the blood. Okay, you've got 0 to 30 centimeters per second in a distance x of 1.77 centimeters. What is the acceleration? V final is 30 centimeters per second. V initial is 0. Distance 1.77 centimeters, so v final squared equals v initial squared plus 2 times a times x. Solve for a.